Assalamualaikum and very good day. So we have actually learned three switching method for the inverter. Okay, so this lesson will be discussing on their advantages and limitations. So the first one that we have already learned is actually what called a square wave, which is the basic switching strategies. And then we have another one which is a quasi square wave, and the most advanced is the PWM switching technique. Okay, so we want to compare these three switching techniques. So the first parameters, or the first actually comparison is actually on the controlling of the fundamental output voltage of the inverter. So if you are using square wave, the output voltage of the inverter can be expressed as 4 VDC over pi, and for the quasi square wave, your output voltage is 4 VDC over pi cos alpha, and for PWM is M modulation index multiplied with VDC. And if you look at the expression, okay, looks like the square wave and quasi square wave, you are not allowed to actually vary the output voltage, okay, because there is no variable that you can actually adjust or tune, okay. But as for example, you have only a constant which is 4 VDC over pi, and for quasi square also you have a constant for VDC over pi, but you have this variable actually cos alpha. But please be noted that this alpha, the variable angle, the variable here is not selected to control the output voltage, but this is actually selected to actually eliminate single harmonics at the output spectrum frequency. Okay, and the only method that is allowed is the PWM, where we have MA here, which is a variable. We can vary. This one is actually a ratio between the amplitude modulation over the amplitude of the carrier. So if you so usually the amplitude of the carrier, which is a triangular, is always fixed. So actually what we change is actually the amplitude of the modulating signal, which is the sinusoidal. So when we adjust the amplitude of the signal, you will have a variable value of modulation index. Okay, so that is the first comparison. So even though you want, for example, but you still, for the square and cos square, you still can vary the V1 here if you vary the VDC, but it is very impossible. For example, if your DC source is a battery or fuel cell, so it is not very easy to actually control or to vary the output voltage of the battery or the fuel cell. So that is the first comparison. The second comparison is on the spectrum, okay, or maybe location of harmonics. Okay, for square wave, so if you plot the spectrum, so you have this one is a voltage output versus the frequency. Okay, you will have a fundamental voltage here, V1, with a frequency of F1. Okay, and the nearest harmonics is appear at 3 times of the fundamental frequency, and this is the magnitude. Okay, so this is actually the spectrum. Okay, and for the quasi square wave, depending on the value that you choose, for example, I choose alpha is equal to 30 degrees. So if I choose alpha 30 degrees, so actually we eliminate the third harmonic. Okay, so if you choose alpha 30 degrees, so the spectrum will be like a square wave. So we have V1 at frequency of F1, and because we select 30 degrees, so the frequency of third harmonic is eliminated. So the nearest one is actually appear at 5 times of the frequency of the fundamental, which is the fifth harmonics. Okay, and we have this one, this same as well. But for the PWM, okay, depending on your modulating frequency, okay, which is the ratio between the frequency carrier over your frequency modulating. So your output spectrum will be, you will have this one, which is V1, which is MA-VDC, and the output frequency here is depending on your F modulating. Okay, and the locations of the harmonics is depends on the, is actually will be available in a cluster. So harmonic cluster here. So this one harmonics cluster, and the location of the main harmonic cluster here is depend on the value of MF. So the frequency is actually MF multiplied with FM. So that is the harmonics frequency. Okay, so usually MF is, for example, if you select MF is equal to 20 and your FM is 50 Hertz. So your frequency, the harmonics will appear at frequency of the harmonics will be appear at 1 kilohertz, which is very, very far from this modulating from the frequency fundamental, which is 50 Hertz. Okay, so meaning that the difference in terms of spectrum. So for the square wave, we have what we call this one. What we call is actually low order harmonics. Okay, this one also we will have a low order harmonics, and for the PWM, there is no low order harmonic because all the harmonic have been shifted at higher frequency. So in terms of design of a filter, okay, so PWM is the least complicated. Is the least complicated. Okay, while for the square wave, you will have need to be make sure that your frequency cut off of the low pass filter should be at around this one, while for the depending and for the quasi square, depending on the harmonic elimination. For example, if you choose to emit the third harmonic, you can actually design your filter to cut before the fifth harmonics. Okay, but for the PWM, as you can see, we have plenty of spaces here because there is no harmonics, so you can actually design your filter to be before 1 kilohertz. So in terms of design, so PWM is the least complicated.